This is John Blyler, SEMICON West 2013. Today I'm talking with Steve Pateras, who is the product marketing manager for Mentor Graphics in their Silicon Test Solutions division. Steve, there's been a lot of talk about FinFET structures. Maybe something folks haven't thought about as much as how do we test these things?
We've been working, in fact, on better ways of testing transistors in general for many months now. We introduced this concept of cell-aware test. See, traditional testing, you look at very abstract fault models, stuck-at faults, transition faults, and these historically have been at the net list level. So looking at a net shorted to 1, shorted to 0. But we never really targeted defects inside the cells or at the transistor level itself. The idea was that by luck, by targeting these more abstract faults, you would ultimately get to defects at the transistor level. It turns out, though, that as we progressed in technology nodes, that wasn't in fact the case. So we were seeing more and more, or the industry was seeing more and more escapes, and a lot more of these escapes were due to defects at the cellular level, at the cell level. So what we decided to do is develop a technology which targets explicitly defects within the cell. And so we call that cell-aware. And the idea is we look at the layout of each cell in the technology library. Using analog simulation, we can determine which patterns are needed to detect those defects. And then we use that information to model those defects in a way that our standard ATPG engines or test generation engines can target and create patterns for those particular defects. And what we found is that we were able to increase the outgoing quality of parts significantly. So sometimes as much as several hundred DPM over traditional patterns.
And this is a tool that the designer would use, again, like perhaps a yield tool, but except for test.
Right. It was DFT engineers, design engineers, even product engineering folks would use our software to generate these very specialized patterns. And now, to extend on that concept, what we found is this cell-level pattern generation ends up being perfectly suited for FinFETs. Because with FinFETs, people are really concerned about defects at the transistor level, more so than in the past. And this technology allows us to model the potential defects within the FinFET transistor. On the fins themselves, we look at leakage defects, drive strength issues. We can model those and then target those explicitly, and hence ensure proper coverage of those defects for FinFET-based technology.
The failures, the defects in the FinFETs, those are from doping that's not quite right, or I mean, what are they? How do they occur?
It's due to a number of different reasons, but what we look at are essentially parametric issues. So resistive, capacitive issues that are out of spec. So a resistor that has too much resistance, capacitor that creates a short, and so those issues are what would lead to typically delay-based defects, and these are ones that we're modeling explicitly and then targeting for coverage.
And by delay, you mean signal delay through because of RC timing, right? Okay.
Unrelated issues, yes. We're excited about this technology. We've seen a lot of silicon results with many of our customers at different nodes. And we encourage people to take a look at it because I think it's something that will be critical going forward.
Excellent. Thank you, Steve.